All right. Now, the last problem, they were nice to us. They told us the data is normal. Cool, I know it's normal. Well, we talked in proportions. How do we know if this data is normal or not? And we said as long as n times p and n times 1 minus p were both greater than or equal to 10, then the data would be approximately normal. Well, obviously that won't work for sample means, because in a sample mean there is no p hat. It's not categorical, it's quantitative. So how can we determine if the data is normal for a quantitative variable? Well, we saw in the example previously about the height of young women that they tell us. Hopefully they tell us, because then it's over. Our job's done. It's normal. Why? Because they told me. But what if they don't tell me the data is normal? How do I know? And if the central limit theorem applies, the central limit theorem sounds pretty simple, super important. One of the big theorems in statistics. Okay? If we take an SRS of size n from any population, doesn't matter. The central limit theorem says that when n is large enough, the sampling distribution of the sample mean x bar would be approximately normal. So if we start looking at sample means and n is big enough, every data set in the world turns normal. It's a magical, mystical thing that happens. Super cool. I wish we were in class, we could do an activity to prove to you that this always happens. For now, you'll have to use these computer printouts and just take my word for it. Okay. Let's look at these 3 different examples. Okay. Up on top in the black is what they're calling the parent population, meaning that, that is the true distribution of the population. So whatever data set this is up the top here, this is the shape. This is what the distribution looks like. Looks just like a straight rectangle. Okay. If I start taking sample means and then plotting all of those X bars, if I take them of size n equals 2, well then, yeah, it kind of looks symmetrical, almost looks like an Egyptian pyramid. But if I start taking samples of size n equals 25, check out what happens. By the central limit theorem, turns into the normal distribution. Super cool. Okay. So it started off symmetrical, but certainly not normal. And then it turned into a normal distribution. Super cool. Okay. Let's look at the second parent population, or the graph of the entire population. It's clearly extremely right skewed, this data set. If I look at samples of size n equals 2, now the distribution's still right skewed, but not quite as strong because we're looking at samples where n is growing. But look what happens when n equals 25. Right back to our perfect bell-shaped normal curve. So the central limit theorem is saying as n gets larger, our sample means, if we take samples where n is large, I wish they would tell us how large. We're going to say 30 or more. If n is of size, and looking at this example, looks like size n equals 25 works as well. Okay? Hopefully we'll have a more exact answer for you later. But when n is large, let's say 25 or 30 or more, any distribution in the world will turn normal. We look at the last one here, this parent population, or the graph of the entire population is clearly not normal. There's actually no data in the middle. It is definitely symmetrical. It looks like it's kind of bimodal and symmetrical. As I start taking samples of size n equals 2, well, now I do have some data in the middle, because if I randomly select them and average them, I'm going to start to hit the true center. And then when I look at size n equals 25, wow, I get the perfect normal bell-shaped curve. So central limit theorem is saying that draw an SRS of size n from any population with a mean mu. The central limit says that when n is large enough, 30 or more, the sample distribution of the sample mean x bar is going to be normal. How do I know if it's normal for a quantitative variable? They tell me, or the central limit theorem applies. Going to be super important for us because we can't do normal calculations if we don't know whether or not the data is normal. Okay? Let's look at an example of this. Okay? The shape of the sampling distribution. If the population distribution is normal, then so will its sampling distribution. If the population distribution is not normal, oh, nice, they did tell us. If n is greater than or equal to 30, then it's going to be normal. Super cool. So let's look at one more example here. Okay. Keith is the manager at a car shop. Based on the records, he knows that on average, it takes his technicians 30 minutes to do an oil change with a standard deviation of 20 minutes. So he knows the population is mu equals 30 with sigma equals 20. These are parameters because they describe the entire population. For a promotion, Keith randomly selects 40 customers and offers them a free oil change. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? Okay. Calculate the probability that the average time it takes to complete the work exceeds 35 minutes. So, what is the probability that it will take longer than 35 minutes on average to complete the work? So that means of these 40 customers that he's going to sample, that on average it takes longer than 35 minutes. Okay. So let's look at the puzzle pieces again. We know that n equals 40. We know that mu equals 30, and we know that sigma equals 20. So what's the center? Well, remember that the mean of x bar equals mu. So the center is 30. What's the spread? The standard deviation of x bar equals sigma over root n. So it's 20 divided by the square root of 40. So the standard deviation is 3.16. What's the shape? Is it normal? Well, n equals 40, which is greater than 30. Therefore, the data is approximately normal by the central limit theorem. We want to know that it takes the probability that it takes on average more than 35 minutes. So we draw our favorite picture, we put the mean, and then we go 1, 2, 3 standard deviations, and then -1, -2, -3 standard deviations on either side of the mean. So the question we're trying to answer is the probability that x bar exceeds or is greater than 35. Well, let's go back to our workhorse, the TI calculator, and let's have it calculate this for us. I want to know the probability. Let me put it in here so we can see them both at the same time. The probability that x bar is greater than or equal to 35. Well, again, distribution, normal CDF. I want to go from 35 to infinity with a mean of, what did they tell us? A mean of 30 and a standard deviation of 3.16. Enter. About 5% chance, 6% chance that it would be longer than 35. So he's pretty safe, probably. He's probably not going to have to give away too many free oil changes. Now, let's look at question B now to finish this idea up. All right, let me clear out of here. How much average time per customer should Keith budget if he wants to be 99% certain that he doesn't go over budget? So they're asking us, it's going to be 99% sure that he doesn't go over budget. So this area in here is equal to 0.99 or 90%. They want to know what should X bar be, or what time should he budget to make sure that there's only a 1% chance that he goes over. Well, we need to go and work backwards now. We know it's normal. We already established that because n is equal to 40, which is greater than 30. So by the central limit theorem, the data is approximately normal. We know the center is at 30 because the mean of X bar equals mu. And we know the standard deviation is 3.16 because we saw that the standard deviation of X bar is equal to sigma over root n. So now we're going to have to work backwards using table A. So 99% sure, that means that there's 1% to the right, 99% to the left. Remember that table A can only give us the area to the left. So if I look up table A, I want to find what z-score corresponds to 99%. So as I go through my handy dandy table A, I see that that is 2.34 or 2.335. So remember, z equals x minus mu over sigma. So z is 2.34. X, I don't know. That's what Keith's trying to figure out. Minus the mean was 30 over the standard deviation, which was 3.16. So multiply both sides by 3.16. So that gives me, what is 2.34 times 3.16? 2.34 times 3.16. Okay, let's call it 7.4. 7.39, we'll call it 7.4. So 7.4 equals x minus 30, because these two canceled out. Now add 30 to both sides, and I find that Keith should budget 37.4 minutes by working backwards using table A. So how much average time per customer should he budget to make sure that he doesn't have to give away free oil changes? He should budget 37.4 minutes per customer to be 99% sure that he's not going to have to give away free stuff. All right, so what did we find out? The mean of p hat equals p. The standard deviation of p hat is equal to the square root of p times 1 minus p over n. The mean of x bar equals mu. The standard deviation of x bar equals sigma over root n. When does this work? Always. When does this work? Okay. Well, if population is at least 10 times sample size. How do we know if it's normal? Okay. For this one, if n times p and n times 1 minus p are both greater than or equal to 10. How do we know it's normal for quantitative data? They tell us, or central limit theorem applies. Those are the big main ideas we need to get out of this unit.